Drainage system for a sports field consists of underground pipes. Situation is modelled with respect to a fixed origin, and according to the model, surface of the sports field is a plane with equation z equals 0. Pipes are straight lines, and one of the pipes, P1, passes through these 2 points, so working in 3 dimensions. A different pipe has a different equation, and then we're asked to determine a vector equation of P1, or the line representing P1. So we've got the origin. I'm just going to kind of go back to the beginning where this comes from rather than just like straight away write the answer down, but it is pretty quick once you've got the hang of it. But we've got the origin. You can write down a position vector to A, which is on the pipe. And then let's draw the pipe in. And then there's another point B along the pipe. So if I want to write down the equation of this red line, then I just need to get onto the pipe, and I can either get on at A or I can get on at B. So I think I went with A, so I could go with OA. And then once I'm on it, I just want to go in some direction along AB, but not necessarily to the point B, which is where this scalar comes in. So that's the equation. Actually, that's the general idea for the equation of any vector equation of a line in 3 dimensions, or in fact in 2 dimensions. So we just need to work out what AB is. And that can be done by going from A to O and then from O to B. That ends up being OB minus OA. So minus 2, minus 8, minus 3, minus 3, 4, minus 2, which gives minus 5, minus 12, minus 1. Now sometimes it's good to, that is just a direction vector. So if there were common factors, you could divide through. And in this case, I'm actually going to make it all positive, so I'm kind of going with BA instead. So I'm going to stick with OA, but you could have gone with OB instead. So I'm going to get R is 3, 4, minus 2. Then I'm going to add lambda times 5. It just makes sense to try and use positives where we can rather than negative. So I've modified slightly, but that is, it's a good point to make that you can do that. There we go. That is the R equation. Determine the coordinates of the point at which the pipe P1 meets the surface according to the model. So this is going to be when Z is equal to 0, because we had that as our plane. So therefore, remember, R is actually X, Y, Z, 3-dimensional position vector. So I'm saying that 0 is equal to minus 2 plus lambda, and therefore lambda is going to equal 2. And I can sub that back in. So the position vector is going to be 3 plus 2 times 5, that's 13. And then 4 plus 2 times 12, that's 4 plus 24, that's 28. And then, of course, we've got our 0. So if I want, that's my position vector. If I want the coordinates, we then write down 13, 28, 0. Now determine the acute angle between P1 and P2, giving our answer in degrees. And the way we want to do this is to use the dot product. So I'm going to need to know a vector in the direction of the first pipe, which I do because it's AB, and then a vector in the direction of the second pipe, which I do not have at the moment. And then I'll be able to use the dot product or scalar product. So I'm just going to draw the other pipe. By the way, I do not know that they intersect. Hey, things can be at angles without intersecting one another. You can still figure it out. Like if you imagine, if you just hold your hands out and one arm is looking like forward and one is going up, yeah, they're not necessarily crossing, but they're at 90 degrees. Let me just draw that. So that one's pointing up and that one's going across. There is an angle of 90 degrees in there, even when they're not actually crossing each other. So this green one could be coming out the page, but what I want is the direction vector of that one, and that will help me get the angle. So what we need really is the vector equation of the line. We've got a Cartesian equation at the moment. We just need to go from that to the vector equation. And because I have these 3 things equal, they're all going to equal some other quantity, which I'm going to call mu. And then I can rearrange them. And again, I'm going through this process like quite slowly, but they're like once you get the hang of it, you can do it really quickly. So I can rearrange x to equal 2 mu plus 1. And I can rearrange y to equal 4 mu plus 3. And then z to equal minus 2 mu minus 1. And from that, I get my equation, because r, which is x, y, z, is going to equal 1, 3, minus 1, plus mu times 2, 4, minus 2. I could actually divide that through by 2, but I'm just going to leave it like that. And once you practice these, you can see it's just, these numbers that end up being part of the vector, the direction vector, and then the others are the position vector. But we took it steady and got there. I don't know why I'm putting a box around it, because actually that's not my answer. That's just like part of the way. So I now have two direction vectors. Find angle between 5, 12, 1, and do you know what? I am going to divide it through by 2. 1, 2, minus 1. Because all I've done is divide that 2, 4, minus 2 by 2. So we've got our two versions of the scalar product. One is that you just do ax, bx, plus ay, by, az, bz. And that just becomes 5 times 1 plus 12 times 2 plus 1 times minus 1. And the second one is that it's the modulus of a times the modulus of b times cos of the angle in between them. The angle in between them is when you have the vectors like this, it's that angle there. Okay, so it could end up being obtuse. We're asked for the acute angle, so we'll see if that one comes out. So I'm going to do 5 squared plus 12 squared plus 1 squared to give me, then square rooted, so to give me the length of a, so that's root 170. And then 1 squared plus 2 squared plus minus 1 squared is root 6 cos theta. Then 5 plus 24 minus 1 is 28. So cos theta plus 28 over root 170 root 6. Okay, which is then 0.8767. Inverse cos of that. By the way, this is going to be obtuse because cos is positive. Gives me, sorry, I have my calculator in radians there, gives me 28.751 or 28.8 degrees. Nice. Finally, and this is the hardest part, we're asked for the shortest distance between the two pipes. So let's sketch out the situation. Got the origin, and I'm getting onto the first pipe, say it's A, and then I'm going in this direction vector to somewhere, and yeah, it could be anywhere along this line. Got my other pipe, let me put it down here. Could be coming out the page. Remember, I'm trying to just draw a sketch in 2D, but it's actually, this is in 3D. So then I'm getting onto my line like somewhere else. And then I'm going along a direction vector. And I want to find the shortest distance. Of course, it looks like they're going to meet, but remember, we're working in 2 dimensions. So I'm just going to draw, say that there, this point here, and this point here, the 2 points that then connect the shortest distance. So I'll label this one C and this one D, because I think I've used capital A and capital B. Now, if you have a straight line and you want to find the shortest distance to a point, what you do is you draw the perpendicular. So if I have any point along D and I want the shortest distance, I would draw a perpendicular from C. But if I then want the shortest distance from D to C, I would also draw a perpendicular from there. And what we're going to end up getting is a line that is perpendicular to both the P1 pipe and P2 pipe. And this is why that is so useful, because once if we can manage to work out CD somehow, might be in terms of parameters. If we then dot product it with either one of the direction vectors from the pipes, it's going to be 0. So let's go for it. I'm just going to write down the vector equation of P1 again. It was 3, 4, minus 2, plus lambda 5, 12, 1. And then for P2, it was 1, 3, minus 1, plus mu. I'm going to stick with the 2, 4, minus 2 rather than dividing it by 2. So if I want to work out CD, what I would do is I'd go back from C to O, which would mean I'd have minus whatever this is, and I'd go from O to D, so then I would add that on. So what I'm saying is I'm going to do 1, 3, minus 1, plus mu 2, 4, minus 2, that's O to D, and I'm going to be minusing O to C, or the same as CO. So minus 3, 4, minus 2, minus lambda 5, 12. Okay, there are two parameters in here, but there's going to be, it's a length between the two lines. So it's obviously going to depend on where the point's on the line. Just want to say that one more time. So I'm just finding the vector CD. So to do that, I'm going back from C to O, which is going to mean I'm going to be minusing this. And then I'm going to be going from O to D, which means I'm going to be adding this. So it's just that second one minus the first one, which is exactly what I've written down here. Okay, now I'm going to sort of bring it together. So I can write that as 1 minus 3, that's minus 2, plus 2 mu, I'm going to write it just as a single vector, minus 5 lambda, and then 3 minus 4 gives me minus 1, plus 4 mu, minus 12 lambda, then minus 1 minus minus 2 gives me 1, minus 2 mu, minus lambda. And this vector will be perpendicular to both 5, 12, 1, the direction vector of the first pipe, and 2, 4, minus 2, the direction vector of the second pipe. So let's dot product them. Therefore, I'm just going to copy it. This dotted with 5, 12, 1 is equal to 0. Okay, it's a bit of a calculation to do here. You have to work really hard for these 5 marks just in terms of how much time it's going to take. Minus 10 plus 10 mu minus 25 lambda minus 12 plus 48 mu minus 144 lambda plus 1 minus 2 mu minus lambda is equal to 0. And you can bring that all together to give 170 lambda minus 56 mu equals minus 21. I'm getting it ready so I can put it in my calculator. So I've got like the unknowns on one side and the number on the other. And then for the other one, this is equal to 0. And you do a similar sort of thing, but it ends up giving 56 lambda minus 24 mu equals minus 10. These two simultaneous equations now. You do not try solving these in your typical GCSE way, trying to make the coefficients equal or even substitution. Just like imagine, look how long that took. So let's just put it in our calculator. Equation, simultaneous equations, two unknowns, and type it in. Carefully, I would add. So we get 7 over 118, that is my lambda, and 131 over 236, that is my mu. So if we now work out CD, we can sub in to here our values, again, carefully, and you should get as a vector minus 70 over 59, 30 over 59, and minus 10 over 59. Which means CD itself, we can use 3D Pythagoras, so square them each, add them, and then square root, and this will give a final answer of 10 root 59 over 59. That is the minimum distance between the lines. Ooh, well done.